Okay, this last thing we're looking at is similar triangles. Similar triangles, here's just a quick example. To talk about similar triangles, we need a little bit of vocabulary. So when we say similar in math or in geometry, it's referring to a pair of figures that are the same shape, but one is larger than the other. But the proportions or the ratios are the same. So if you imagine if we copied and pasted, so if I take this and I copy and paste and make it bigger, it will look like this. It's the same proportions. It's just bigger. Same here. Same proportions, just bigger. And that's what we mean when we say similar, which is not the same thing we mean when we say similar in real life. When we say similar in real life, we mean, oh, they're like kind of close to each other. Similar in geometry is telling us they are proportionate to each other. So we often use this Greek symbol delta to talk about triangle, and it looks like a triangle, so that's helpful. And this is telling us that triangle ABC is similar to triangle DEF. And the order is really important when we're naming triangles. So notice I said A, B, C. So I went from here to here to here to here. It's similar to D to E to F. Triangle ABC is not similar to triangle EFD. So that's important, and it might seem confusing right now, but we'll get to a point where it'll make more sense, hopefully. So what this is telling us is that this line, A to B, this line here, is similar or proportionate to this line, D to E. So these two lines are proportionate to each other. And then line B to C is proportionate to this line E to F. And then line C to A is proportionate or similar to this line F to D. So that's why, part of the reason why naming is important. Now when we look at this and we see, okay, triangle ABC is similar to DEF. Well, I'm looking at this and I know the length of this line and this line, but I don't know the length of this line. What I do know on the other triangle is this line and this line, but I don't know this line. And I can use a proportion to help me out here. So if I'm looking at this triangle ABC, and I'm going to say, okay, 11 over X. So that's my AB and AC. AB over AC. And if I know that these two triangles are similar, I'm going to take this same line, DE is 22, and DF is 24. So I'm taking the same lines, the similar lines from each triangle, and setting them up as a proportion. And then I can use my cross multiplication where I have, okay, 11 times 24 equals X times 22. 264 equals 22x, and I'm going to divide both sides by 22. And I know that x equals 12. So now I know that this line here equals 12. And I can do the same thing here to find out what this one is, because I know what it is on the other triangle. So I could set it up, and now I can choose whichever lines I want. I can do 12 over 8, or I can do 11 over 8, or I can do 8 over 11, or 8 over 12. It doesn't matter which lines I use as long as I use the same lines on the other triangle. So I'm going to go 8 over 12. So this BC over CA, which means on my equivalent, I have to use this EF over FD. And I can cross multiply again. So I have 8 times 24 equals 12y is 192 equals 12y divided by 12 on both sides. And I get y equals 16. Pause this video and give this one a try. All right, so if I have 22 over x equals 99 over 90, right? So I have the bottom over the side equals the bottom over the side. It doesn't matter which order I put these in, again, as long as the order is the same on both sides of the equal sign. So I have, 22 times 90 equals x times 99. 1980 equals 99x. Divide both sides by 99. So x equals 20. All right, so here we're showing that similar triangles might not always be oriented in the same direction, and this is why their naming is so important. So this is telling us that triangle BIG is similar to triangle MOP. So this second triangle is kind of rotated. So what's important here is for us to know that this line B to I, so this line here, is proportionate or equal to this line M to O. So even though they're not in the same spot in the way that the triangles are oriented, they are in the same spot in the ways that the triangles are similar to one another. So naming is so important here. And then IG is similar to OP. Unfortunately, I don't know what OP is, so I can't use that line to help me find my answer. But GB is equal to PM. So now I can swap this out with the information I know. So BI is V, that's my variable. GB is 54. MO is 69. And PM is 81. And from here, I can cross multiply, where I have V times 81 equals 54 times 69. So I have 81V equals 3,726. I'm going to divide both sides by 81, and I get that V equals 46. So this line here, the length is 46 inches. In a similar way, if there's a line that's drawn through a triangle so that it's parallel to one of the other sides, its segments are proportional lengths. So what we're really saying is we have this small triangle here is proportionate to the big triangle here. And we can use that information as well to help us find information we don't know. So let's take, for example, here, right? I have a small triangle here, and then I have the big triangle here. And I'm trying to find X, the bottom of the big triangle. So I know that the side over the bottom equals the side over the bottom. I'm going to say the side of the big one over the bottom of the big one, and the side over the small one over the bottom of the small one. So if I know the side of the big one, Here's this side. I have 5 and 7. If I add those together, I get 12. And the bottom of the big one is x. That's the one I don't know. The side of the small one is 7. And the bottom of the small one is also 7. So I can cross multiply here. 12 times 7 equals x times 7. 12 times 7 is 84. 7x, divide both sides by 7, and I get 12. X equals 12. So this bottom piece is 12 units long. Pause this video and give this one a try. Okay, so again, I have this big triangle and I have this small triangle. And I'm trying to find the side of the small triangle. Here is going to be a little trickier because I don't know the side, the complete side of the big triangle. So I'm going to write it like this, where I have the side of the big triangle is 3 plus x, and the bottom of the big triangle is 16. And then the side of the small triangle is x, and the bottom of the small triangle is 8. Well, now I'm cross multiplying here. And this part's going to get a little bit weirder. So I have 16 times x. That's where we've been this whole time, right? But then I have 8 times 3 plus x. So what I really have is 8 times 3, which is 24, and 8 times x, because I still don't know what x is. Well, now I have an x over here and an x over here. So I have 16x equals 24 plus 8x. I want all of my x's to be on one side and all of my numbers to be on the other side. So what I'm going to do here, since I'm adding 8x over here, I'm going to subtract 8x. And if I do it on one side, I have to also do it on the other side. So now I have 8x equals 24. And I can divide both sides by 8, and I get that x equals 3.